going to practice our implicit differentiation. Okay, and the way we go about this is the following. We need to recall the distributive property of derivatives, and what that says is the following. If I have a function f plus g, then the derivative of this, it's going to be write it like this, f prime plus g prime. But recall that f prime of x is the same thing as let's say df dx. This is another notation for derivatives, and for implicit differentiation we like to choose this notation. All right, cool. One thing that, and just to mention, the reason why we like this, it's because this tells us the bottom, the denominator, it tells us what we are differentiating with respect to. Since the denominator here it's dx, this tells us that we are differentiating with respect to x. Fine, let's start the problem. So here I'm just rewriting, okay, and I want to differentiate first with respect to x. And what that says is like, hey, let's use this d notation. And by the way, this is called operator. You can think of it as an operator for those who have taken more advanced mathematics. So I'm going to write d over dx on both sides. And I'm going to work on it simultaneously. So here I'm going to distribute the derivative operator. So I get d over dx x squared plus d dx y squared. And then on the right hand side, the derivative of a constant is just 0. So just make it 0 right off the bat. Now I want to point something out for this next step. Notice that these variables are the same. When you are doing implicit differentiation, if the variables match, you differentiate as normal. So the derivative of x squared is just 2x. Cool. Now for the second term, the derivative here, it's the variables x, it's y, it's different. So we differentiate as normal. So the derivative of y squared, it's 2y. But because the variables are different, we have to put dy over dx. The variable, we differentiate it with respect to, remember, it was with respect to what? X. This is why we have to write dy over dx, because they're different variables, equals 0. Now, the final step is for this problem is that we need to now solve for dy dx, i.e. we want to treat this as an algebraic equation, and the goal is to write dx equals blah blah blah. In other words, we want to have dy over dx on one side and everything else we kick it to the right. Okay, so let's do that now. So here, rewriting the problem again, the 2x, we don't want that, so we want to move it to the other side. So in algebra, to move things across the other side, across the equal sign, is we do the opposite of what it says mathematically. So instead of positive 2x, I'm going to subtract minus 2x on both sides. So I get 2y times dy dx over negative 2x. Great. So now, but I don't want 2y times dy over dx, so I'm going now divide by 2y on both sides. So I get dy dx equals negative 2x over 2y. And simplifying this, I get negative x over y. And we basically differentiate it with respect to x. Great. Now, let's do the same problem, but this time, let's differentiate with respect to y. So I'm going to write d over dy on both sides. And remembering that when I differentiate with respect to something, that goes in the denominator. Cool. So now I'm going to apply the distributive property of derivatives. So here I get 2 dy x squared plus d dy of y squared. And the derivative, again, the derivative of a constant is just 0. So I put 0. Now notice here that the y and x's, they're different variables. So I'm going to differentiate as normal, but I'm going to add the extra step. So remember, d, whatever the variable is, x over with respect to what we differentiated by, which is dy. Then here, for the second term, notice that the y's, they're both y's, right? The same variable. So we just take the derivative as we typically do. So it's 2y. So I do not add the extra part because they are the same derivative. They are the same variable. Fine. So now again, I want to solve for dx over dy. So I'm going to move things across the equal sign. So I'm going to subtract negative 2y on both sides. So I get 2x times dx over dy, which equals negative 2y. And now I'm going to divide both sides by 2x. So I get dy, sorry, keep writing dy, dx over dy equals negative y over x. Now, like, what if I have 3 variables? What if I have x, y, and z? So how do I go about this? For one, we have to choose with what variable we are differentiating with respect to. So here I'm going to say with respect to z. So when I take the derivative, I'm going to write d over what? dz. So now I get x. I'm just rewriting the problem right now. And again, for the right hand side, the derivative of a constant is just 1. So the derivative of a constant is 0. So it's 0. And again, I'm going to apply the distributive property of derivatives. So I get d dz x cubed plus d dz of y cubed plus d dz of z cubed. Okay, cool. Notice that the z's and the x's are different variables, so I differentiate as normal. So the derivative of x cubed is 3x squared, but I have to write the extra part. Remember, whatever the variable is, you write it on top, and whatever you differentiate with respect to is at the bottom. We're going to do that for the second term. So the derivative of y cubed is 3y squared. And again, because the variables are different, I'm going to write the name of the variable here, which is y, divided by what the variable that we differentiate with respect to. Then for this one, since the z's are it's the same variable, I differentiate as normal, but we don't add the extra part. Cool, 0. So now this would be the problem in here. We will probably try to solve for them, but since we have 2 different ones, let's just leave it as is. Fine. So we are done. And the reason we left it as is because I wanted to demonstrate to you that, hey, because a big question that's always asked when students are learning this, it's like, hey, when do I add the d over dx? When do I add the d over dy? So I just wanted to emphasize that you add the extra term, like you add the extra term by extra term. I mean just the derivative part when the variables are different. But if they're the same, you differentiate as is, but do not add the extra part. Cool.